Greetings everyone, welcome to Ken Academy. In this video, we will try to solve this problem right here, which involves a supersonic wind tunnel sketched on the right side. Now, the supersonic wind tunnel has an air temperature and pressure in its reservoir of 1000 Kelvin and 10 atmospheres respectively. And the static temperatures at the throat and exit are 833 Kelvin and 300 Kelvin respectively. Now the mass flow through the nozzle is 0.5 kilograms per second. And the constant pressure specific heat of air for this problem right here is 1008 joules kilograms Kelvin. This problem wants you to calculate for the velocity at the throat section of the wind tunnel, the velocity at the exit, and the area of the throat and the area of the exit. So before we go diving right into the problem, let us try to have a brief background about our supersonic wind tunnel. So our supersonic wind tunnel has a reservoir right here, and this is the inlet section. This is the converging section, and then we have our throat of the wind tunnel, and this is our diverging section, and this is our exit section. Now, it is indicated right here in this figure that the velocity of the substance, which is air, is negligible or equal to 0. And in the converging section, in our converging section, the flow is subsonic, meaning to say the flow is less than the speed of sound. And at the throat, indicated right here, m equals 1, which is the Mach number. And it is said right here in the problem that the Mach number is equal to 1 in the throat, which means to say that the flow of air is equal to the speed of sound. Now in our divergent section, the flow of air is given by m greater than 1, which means to say that the Mach number is greater than 1, which also means to say that the flow of air is greater than the speed of sound. The flow of air becomes supersonic. So the problem is asking for us to solve for the velocity at the throat, and we know that the velocity of air in this region is equal to the speed of sound. So we are trying to solve for that value. What is the speed of sound in the given current conditions? And we are also looking for the velocity at the exit. We are also looking for the area of the throat and the area of the exit. So to begin with our problem, let us write down our known given. Okay, so our known given, let us begin with our reservoir, R, or let's just use the appropriate symbol, O. Right? Now the temperature in the reservoir is 1000 Kelvin. Pressure is 10 atmospheres, right? And also in the throat section, temperature becomes 833 Kelvin. And in the exit section, temperature becomes 300 Kelvin. We also know that the mass flow rate through the wind tunnel nozzle, which is the whole thing, is given by 0.5 kilograms per second. So the mass flow rate on this area, in the throat section, is still 0.5 kilograms per second. And on the exit side, the mass flow rate is still 0.5 kilograms per second. And we also know that the CP, or the constant pressure specific heat of our substance, which is air, is 1008 joules kilogram Kelvin. So in our first problem right here, we are looking for the velocity at the throat, since we have known givens of temperature at the reservoir and at the throat, and we know velocities at the reservoir, and we are looking for the velocity of the throat. The equation that we are to use is the compressible flow energy equation, as it relates temperature and velocity of two differing regions in the flow. So let's begin writing down our solutions right here. Right? So what is our equation again? It's the compressible flow energy equation, and it's given by CPT1 plus V1 squared over 2 equals CPT2 plus V2 squared over 2. 1 being our reservoir and 2 being the throat. Okay, this is 1, this region right here is 1, this region right here, that one is 2. So let's try to solve for that one by simplifying our equation further. Now we're looking for V2, or the velocity at the throat. We know CP, we know T1, we know V1. V1 is the velocity at the reservoir, which is 0. And we also know CP, we also know temperature 2, which is the temperature at the throat, which is 833 Kelvin. We are looking for this one. So let's just simplify the equation. CPT1, V1 is 0, so I'll try to not include that here. I will transpose CPT2 to the other side. I am left with V2 squared over 2. Now to remove 2, I will multiply both sides of the equation by 2. And to remove the squared right here, I will get the square root of that, of both sides of the equation. Alright, so I am left with V2 equals two times, CP is common for both terms, CP times T1 minus T2. That is how I'm going to begin with my equation. So let me continue on by substituting the known values of each variable. 2 times 1008, and we also have T1, which is 1000. Alright, minus 833. Take note, guys, I have not yet written the units. So this one, let me just pull out my calculator. This one, let me just write that down again. Let me begin with solving for this one. 1000 minus 833 is 167 multiplied by 1008 multiplied by 2. We get the square root of 336 672. And if we get the square root of that one, we get 580.23 velocity at the throat. Now, how do I know if my units will come out correctly after all that operation? So let's do a separate operation for our units. Now, we will still be using the same equation, and we will remove all the numerical values. Right? So the square root of the values or the units of CP, which is joules, kilogram, Kelvin. Let me write that down properly. Multiplied by the units of temperature. Cancel that one out. And I also know that joules is equal to Newton meter. Let me continue with that one. Newton meter kilogram. Right? I also know that 1 Newton is equal to kilogram. 1 kilogram accelerated to an acceleration of 1 meter per second squared. So I will substitute that one. Right, so kilogram times meter per second squared multiplied by meter over kilogram. Cancel that one out. We get a square root of meter squared per second squared. And if we get the square root of that one, we get the appropriate unit, which is meters per second for velocity. So this is just the solution for question A, which is asking about the velocity at the throat. Now, since it is said here that the velocity at the throat becomes, the Mach number at the throat becomes 1, meaning to say that the velocity of air is at the speed of sound, which is 580.23 meters per second. Now, that is not the standard sea level speed of sound. Okay, take note of that one, guys. This is just the speed of the sound at the given conditions.